Lesson 4. Training a neural network. How does it actually work? Hello. In the previous lesson, we explored how weight updates are performed in a neural network using derivatives and a learning rate, and we demonstrated this with a simple example involving a single weight. Now, we'll dive into training a real network with data, layers, hyperparameters, and graphs. To understand how a network actually learns, we'll introduce 4 critical concepts. The first is the batch. Instead of feeding the entire dataset into the network at once, we divide it into smaller units, batches. If I have 10,000 examples and a batch size of 32, then at each step the network only sees 32 examples, calculates the output loss, computes the gradients, and then performs the update. This approach is called mini-batch training, and it makes training faster, more memory efficient, and sometimes even statistically more stable. An epoch is a complete pass over the entire dataset. If we use a batch size of 32, it will take 313 updates to complete one epoch on a dataset of 10,000 examples. Usually, networks are trained over dozens or even hundreds of epochs, and these determine the pace at which the model progresses.
If after 20 epochs the price doesn't change, I don't continue. I stop the training and check what isn't working.
While the gradient shows the direction of improvement, the learning rate ETA determines how far we go with each step. If the value is too small, the network will converge slowly. If it's too large, it can cause oscillations or even divergence. Choosing the right learning rate is essential for stable and effective optimization. Optimizer, the mechanism actually responsible for updating the network's parameters. It receives the gradients calculated during backpropagation, combines them with the learning rate and sometimes with historical information, and performs an adjusted update to the parameters. The simplest one we saw earlier is gradient descent, but today there are advanced optimizers like RMSProp, ADAM, and AdaGrad that also take into account momentum, accumulated gradient variance, and individual adjustments for each parameter. We'll look at advanced optimizers later on. Now, let's see how the parameters affect convergence. To see how each of the components affects things, we'll run a simulation on simple data. In the first graph, you can see the effect of the optimizer type on the decrease of the cost function. ADAM, shown in black, converges quickly and smoothly. SGD, in blue, goes down at first but suffers from volatility. RMSProp, in gray, is somewhere in the middle. It's clear that ADAM makes efficient use of the gradient and reaches an accurate result faster. In the second graph, learning rate, you can examine 3 different values, where the high rate in black causes volatility and even jumps. The very low rate in gray converges slowly. The medium rate in blue shows a good balance, converging quickly and steadily. Now let's look at the batch size. When the batch is small, shown in black, there's a quick but volatile response. When the batch is medium, in blue, you get both stability and speed. When the batch is large, in gray, the process is very stable, but it converges slowly. The choice depends on balancing performance and computation time. To sum up, batch controls the size of the data in each pass. Epoch measures how many times we've gone over the entire dataset, and learning rate determines the size of each step. The optimizer is the mechanism that processes the gradient. Each one is critical, a small change, and the result could be either an accurate model or a failure. In the next lesson, we'll focus on evaluating the model's performance.